Hello and welcome to the lecture on fundamentals of electric drives. In the last lecture, we just started the discussion on induction motor drive, and we saw that there is a slip which is present when the induction motor rotates. Now, the slip is defined as the ratio of omega ms minus omega m and omega ms. Omega ms is the synchronous speed, and how do we define this omega ms? If we define this in radian per second, this will be 2 f by p into 2 pi if we define in radian per second, or if we define this in rpm, this is 2 f by p into 60, this in rpm, revolution per minute, and this is same as 120 f by p, and the unit is rpm, and this unit, the above one, is radian per second. Now, what is f here? F is the frequency of the input supply. We are supplying the input with some voltage, and the voltage has the supply frequency, that is f. And what is p? P is the number of poles. P is the number of poles, of induction motor. So, this is the speed at which the rotating magnetic field rotates. Since we have A, B and C, we have 3 different phases. When you apply a 3 phase voltage, the magnetic field rotates from A to B to C, and the speed of that is given by 2 f by p into 2 pi in radian per second, or 120 f by p in rpm. Now, let us redraw the equivalent circuit. We have already seen that this is the equivalent circuit, which is the per phase equivalent circuit. Although we have 3 phase, we can draw it per phase, which is sufficient to do the calculation. Now, this is the magnetizing reactance. This magnetizing reactance can be sometimes moved to the input side. So, we get another circuit which is given as the resistance, the reactance of the rotor resistance, and this magnetizing reactance is moved to the input side. So, this is JXM, and this is the stator resistance, the stator reactance, the leakage reactance of the stator, the rotor reactance referred from the primary side, the resistance of the rotor referred from the primary side by the slip, and here we apply the voltage, the per phase voltage, AC voltage. The input current here is Is. The current which flows through the rotor is called IR prime, and the current which flows through the magnetizing branch is IM. Now, this is called the approximate equivalent circuit. This approximate equivalent circuit is fairly accurate for the calculation to find out torque and speed of the motor. Now, let us try to find out the torque and the speed. Now, here we have the air gap. So, this part is the stator and this part is the rotor. And the induction motor can be thought of a rotating transformer. So, the power which flows from the stator to the rotor is called the air gap power. This is called PG. Now, what we see in the rotor circuit, we have a reactance, we have a resistance, and the power which is an active power is verily the power consumed by the rotor resistance, that is R r prime by S. So, we can write down the air gap power as I r prime square into R r prime by S. Now, this is for a single phase circuit, since we have 3 phase, we can multiply by 3. Now, what is I r prime? I r prime is the rotor current referred from the primary side. So, this I r prime can be evaluated. We have applied a voltage, that is V here is AC voltage, and we have an impedance in this case. So, I r prime is equal to the applied voltage V per phase divided by the resistance of the stator, the resistance of the rotor, plus the leakage reactance of the stator and the leakage reactance of the rotor. So, this is the rotor current, that is I r prime. Now, what about the copper loss? The copper loss in the rotor we define as P r C u is the rotor copper loss. The rotor copper loss is essentially equal to the rotor current into the actual rotor resistance. Now, this resistance can be broken down into 2 resistance, one is R r prime and the other resistance is R r prime into 1 by S minus 1. So, this is a physical rotor resistance, and this resistance is a fictitious resistance. Now, in an electric circuit, when we try to derive the mechanical power, we have to have a means of finding out the mechanical power. Slip is a mechanical variable. So, this part involves slip. So, this represents the mechanical output. So, we can say that resistance representing mechanical output. Now, we have the rotor copper loss, which is I r square R r, and since we have a 3 phase circuit, we can multiply by 3. So, we have in this case the air gap power, and part of this goes as rotor copper loss. So, that is P r C u. So, the power which comes out of this is the mechanical power, that is P mechanical. So, P mechanical is equal to the air gap power crossing the air gap minus the rotor copper loss, that is equal to 3 I r square R r by S minus 3 I r square R r prime. Now, that is equal to 3 I r square R r prime into 1 minus S by S. And how do you find out the torque? Because ultimately what we have to find out is the motor torque. So, the motor torque T is equal to the mechanical power by the mechanical speed. So, in that case, that is equal to 3 I r square R r into 1 minus S divided by omega m into S. So, that is equal to 3 IR square RR prime. We can replace this quantity by the synchronous speed. So, as we know before, the slip has this relationship, or we can say that from this we can say that omega m is equal to 1 minus s into omega ms. So, from this equation for the slip, we can find out the mechanical speed, which is 1 minus s into omega ms. So, when we substitute for omega ms, this 1 minus s gets cancelled. So, what we get here is omega ms into s. So, this is the torque of the induction motor. Now, let us see how we can write the expression for the torque. So, T is the torque output, which is given as 3 IR square by omega ms into RR prime by s. What is IR square? 3 into V square divided by RS plus RR by S whole square, because we have the value of IR here. This is in the phasor quantity. We want the absolute value of this. So, we have to divide by impedance here, and this is what we are trying to do. IR square is V square by RS plus RR prime by S whole square plus XS plus XR square. This is the square of the current. We have the synchronous speed that we can write it here into RR prime by S. So, this is the torque of a 3-phase induction motor, the average torque output of a 3-phase induction motor. Now, we need to find out the characteristics, we need to plot this. So, what we do here, we will find out, is there a maximum torque available. So, for maximum torque, the right hand side we have one variable, that is slip. This is the only variable we have. The voltage is fixed, the synchronous speed is fixed, we are having a fixed voltage and fixed frequency supply. The voltage is fixed, the frequency is fixed. The resistance, the stator resistance is fixed, the rotor resistance is fixed, the stator and the rotor reactances are fixed. So, the only variable in the right hand side is the slip. So, for the maximum torque, dt by ds has to be equal to 0. So, we will substitute for this, we derive or we differentiate the torque with respect to slip and equate that to 0. And when we equate that to 0 and simplify, we get the slip for maximum torque. Slip for the maximum torque is given as x max t, which is equal to RR prime divided by under root RS square plus XS plus XR prime whole square, and this could be plus or minus. So, what we get here is that the maximum slip is given by plus minus RR prime by under root R square plus XS plus XR prime whole square. It means there is a positive slip, there is also a negative slip. So, there is a possibility that an induction motor can operate for positive value of slip, it can operate also for a negative value of slip. Now, if we substitute this value in the previous equation, let us say this is equation number 1, this is equation 2. Now, if we substitute the value of slip in equation 1, what we get here is the maximum value of torque, T max. So, T max is torque at S equal to x max t. So, if you substitute S equal to x max t, what we get is T max, and that is equal to 3 V square divided by R s plus minus R s square plus x s plus x r prime square, and then that is by 2 omega m s. So, the maximum value of torque is given as 3 v square by 2 omega m s into R s plus minus under root R s square plus x s plus x r prime whole square. Now, we can draw the torque slip characteristic of an induction motor. So, if we draw that, or if we draw the torque slip or torque speed characteristic, we can plot this equation 1. We get the torque speed characteristic in the following fashion. In the x axis, what we have here, we take the torque. In the y axis, we take the speed. And you know the speed and the slip are related. Omega m is equal to 1 minus s into omega m s. So, the slip and the speed are related. So, this is the no load speed. Let us say this is omega m naught or omega m s here, the synchronous speed. This is minus omega m s. So, usually this equation 1, if you plot this equation 1 for various values of slip, we get this curve, and this is the speed in the y axis. So, the slip value is equal to 0 here, and slip is 1 here, and here the slip is more than 1, and this is the negative slip. So, usually this zone is called forward motoring. So, normally the motor operates in this particular region, that is called forward motoring. So, if we increase the speed of the motor beyond the synchronous speed, we go for generating operation. This is called forward regenerative braking. So, this part is for negative slip, which is for regenerative braking. If we use the motor in that region, the motor will be operating as a generator. The energy will be fed to the AC supply. Now, if we change the phase sequence of the motor, suppose the phase sequence in this case is ABC. Now, if we make the phase sequence ACB, we change the direction of the rotating field. So, instead of plus omega m s, the rotating magnetic field will have a value that is minus omega m s, and then this region will be for the reverse motoring. This is third quadrant, and this region will be called the reverse regenerative braking. So, we have the first quadrant, which is for the motoring, and we have the second quadrant is for the forward braking, and in the second quadrant we have this characteristic which is basically for plugging. This is called forward plugging. The slip is in fact is positive here. So, it is forward plugging, and similarly here if we extend the characteristic to the fourth quadrant, we call this to be reverse plugging. So, this is the complete torque speed characteristic of an induction motor, both for the forward and reverse operation, forward motoring, forward regenerative braking, forward plugging, reverse motoring, reverse regenerative braking and reverse plugging. So, this has come from the equation 1 for forward motoring, and if we make the speed of the synchronous speed or the speed of the rotating field negative, we get reverse operation. Now, let us see what is the behavior of the motor. Usually what we do, we supply the induction motor from a 3-phase balanced supply. So, what is the balanced supply? We have 400 volt. In that case, the per phase voltage is 230 volt and the phase sequence is ABC. Now, we will discuss if the supply voltage has got harmonics. Analysis of 3-phase induction motor fed from non-sinusoidal supply, non-sinusoidal supply. So, in this case the supply voltage has harmonics. Say for example, if we supplied from an inverter, a square wave inverter, phase A, phase B and phase C will have harmonics. Say our phase A is not a sine wave, but it is a square wave like this. This is a waveform for, let us say, phase A voltage. What about phase B? Phase B is shifted from phase A by 120. This is 180 here pi and this is 2 pi. So, the phase B voltage will be like this. This is phase B voltage and the x axis is omega t. What about phase C? Phase C will be shifted from phase B by 120. So, in that case phase C will start from this point. So, this is phase C voltage which will look like this. So, the input, this is phase C voltage. So, the input voltages are not sinusoidal, they are square waves. So, square waves means they have harmonics other than the fundamental. So, we can have Fourier series to separate the fundamental, the third harmonic, the fifth harmonic, the seventh harmonic and so on. This waveform, which is a square wave, will have all odd harmonics. So, usually the voltage has odd harmonics due to quarter wave symmetry. So, if we see here 1/4 of the cycle, this is called the quarter wave. So, this is the mirror image of the left hand side is the mirror image of the right hand side, that is called quarter wave symmetry. So, because of the quarter wave symmetry, the supply voltage will have odd harmonics. So, let us say that we have phase A voltage. So, phase A has got a fundamental component, that is V1 sin omega t, and phase B fundamental is V1 sin omega t minus 2 pi by 3. We have 3 phase voltages, and the fundamental of phase C is V1 sin omega t plus 2 pi by 3. Let us say that we talk about the triplet harmonics, the third harmonics. What about the third harmonics? V A n 3 is equal to the amplitude of the third harmonic voltage V 3, which we can find out by Fourier analysis. Here sin 3 omega t, because the frequency of the third harmonic is 3 times the fundamental. Similarly, phase B here, B n 3 is equal to V 3 sin 3 omega t minus 2 pi by 3, that is equal to V 3 sin 3 omega t once again. And what about V C n 3, the third harmonic of the phase C, V 3 sin 3 omega t plus 2 pi by 3, that is equal to V 3 sin 3 omega t. So, what we get here is that the third harmonic voltages V A n 3, V B n 3 and V C n 3, they are co-phasal, they are basically in the same phase. So, when a voltage is co-phasal, that voltage or that set of voltages will not produce any rotating field, and hence the third harmonic voltage has no role in torque production. So, third harmonic voltage does not produce any torque. And this is the positive sequence, which means the sequence is ABC. Now, similarly, we can find out the fifth harmonic voltage. So, we can write down V A n 5, V B n 5 and V C n 5, and they will be respectively V 5 omega t, V 5 sin 5 omega t minus 2 pi by 3, V 5 sin 5 omega t plus 2 pi by 3. If we simplify this, phase B voltage will be V 5 sin 5 omega t plus 2 pi by 3, and the V C n 5 will be V 5 sin 5 omega t minus 2 pi by 3. So, this has got negative sequence. So, the fifth harmonic voltages will result in a negative sequence voltages, that is the rotation is not A B C, but from A to C to B. So, this is how the various harmonics produce their respective field in the air gap of the induction motor. So, we will continue discussing this harmonics, the effect of harmonics on the operation of induction motor in the next class.